Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started. So I'm happy to introduce Benjamin Livshits. Benjamin is a student of Monica Lam at Stanford, and he just defended his thesis a few months ago, so I guess I should call him Dr. A few weeks, okay. Dr. Livshits.
Thank you.
And, you know, he's an incredibly productive guy. I think he published like 11 papers last year, so he'll try and tell you about some of them and some of his work on improving software security in the next R&R. So go ahead.
Thank you for the introduction, and thank you all for coming here. So, computer security has attracted a great deal of attention in recent years, and not a week goes by that we don't hear about a new vulnerability being discovered or a website broken into. And as you can see from this graph, there is no sign of decline as far as the number of vulnerabilities is concerned. So this is something we get from the NIST database. Now, according to this quote from the Gartner Group, most of the vulnerabilities out there happen at the application level, at a higher level, as opposed to the network level. Over 70% of all attacks that they studied, in fact, happen at the application level. Now, once this, even though this is clear, it wasn't really entirely obvious to us what kind of vulnerabilities were most common. So we decided to go and study this question for ourselves. So I went to this website, securityfocus.com, that collects vulnerability reports, and collected a sample of about one week's worth of vulnerability reports. So about 500 vulnerability reports total. And this is how they can be classified. So what you can see here, actually, is there a pointer? Does this work? Not so much. Okay, can you play with this? Here. So as you can see from this, by far the most common issue, the most common category of vulnerabilities. Oh, great. By far the most common category of vulnerabilities are ones that come from input validation. So they account for more than 50% of all of the vulnerabilities in this sample. Now, when we narrow down on just those vulnerabilities, this is the picture we get. Okay, so again, there are many different sort of subcategories in this group, and the infamous buffer overrun issue comes in a distant third. And essentially, all of the, well, most of the other issues are issues specific to web applications. So you see issues with fancy sounding names here like SQL injection and cross-site scripting attacks and the like. Now, you might be wondering what a SQL injection is. So let me just show you. Yeah, go on.
You snapshot that 1 week.
Mm-hmm.
Did you go forward or back to look time? I guess one of the reasons I'd ask is I would assume that, for example, when someone figures out a new vulnerability, there tend to be a rash of attacks.
Right.
And so are you looking at a blip that happens to fit well with the thesis you're trying to attack, or is this actually representative of across a period of time?
Yeah. Well, good question. It's pretty representative, that's the belief. Now, the exact numbers will differ quite a bit, actually, depending on what source you go to. So we looked at several databases, and the numbers vary from maybe almost 60% we saw in this case to 70% to 55% and so on. So I'm not claiming these to be sort of the most accurate numbers, but at the same time, I think it's pretty much a trend. And most of the things here are pretty much stabilized, as you'll see shortly. Now, let me talk about the SQL injection vulnerability. So I have an example here of a web form on a site somewhere. Okay, and the idea behind web form is that so the user enters his login and password, and then there is a Java J2E web application beneath, on the server here serving these requests. And within the application, you might have a piece of code that looks like this. So you have a way to get the username from the form over here. I can't point it. Okay, there. The username over here, the password over here, and then there's a SQL query that is constructed by using string concatenation over here. And then finally, the last step in this process is that this query is being submitted to backend database for processing. Okay, so far so good. Now, suppose Bob comes along and enters Bob's password, and that makes it into the application on the server. This is the query we'll get. Okay, and then Bob clicks submit, and he gets his information back. So this is looking up his account details or something of that sort. Okay, so far so good. Now, suppose I come along as a malicious hacker and try this. Okay, so I enter Bob apostrophe double dash. Now, what you need to know is that at least in the Oracle dialect of SQL, double dash indicates the beginning of a comment. So essentially, the rest of this command that is going to be passed to the database for execution is going to be effectively ignored. So I click submit, I get Bob's information. So without knowing anything about Bob's password, I was able to pretty easily get at his private data. Now, suppose I'm even more evil than before. So I come along and I type this in. Okay? Now, this is the query that's constructed that goes into the backend database. Now, when the SQL database interprets this stuff, it's going to essentially look at it as two separate SQL queries. The first one is going to do a select, and the second one will execute this command, which is a command that deletes the user's table. Well, as you can probably see by now, nothing good is going to come out of this. Now, to summarize, basically, by controlling the input that goes into the application, I was able to both get at private data of a user and also to remove and affect data that's stored in the database. Now, SQL injection is but one of many web application exploitation techniques that exist out there. There's a whole range of them. So some of them are shown over here, and all of them have these fancy sounding names. Now, fortunately for us, there is quite a bit of structure in this picture. So there's an easy way to classify all of these web application attack techniques. So it turns out that some of them have to do with how malicious data is injected into the application. So there are several of those, and they are treated as essential taint sources in this case. And then there are several ways to exploit this malicious data once it's in the database. I'm sorry, in the application itself. So any particular vulnerability, any particular exploit is essentially a combination of these two. It's like a menu, right? You get something from the first category, like parameter manipulation, and parameter manipulation is essentially changing fields of a web form. And you've got the second part, which is SQL injection in this case, which is what I described just now. And a combination of these two gives you vulnerability. Now, to go back to Galen's question, actually, these issues, these vulnerabilities have a pretty short but very illustrious history. So I actually went back and tracked down the first report about cross-site scripting. It goes back to year 2000, and then SQL injection is around the same time and so on. And then there are some sort of more fancy forms of attacks that appeared a little bit later on. Now, despite having a pretty short history, there's been a number of very important exploits that go along these lines. So let me give you sort of a little snapshot of some of them. So these issues go back only a few months. So the most recent one is in May 2006, which was, I think, a worm that was in the Yahoo email system. Now, there are also financial impact numbers that are associated with these exploits, and the average cost per incident is estimated to be more than $300,000. And the total cost of the overall cost of online fraud is estimated to be $400 billion a year with a B. So this is a what I'm trying to say here, the takeaway message here is that this is a big practical problem that is affecting a lot of applications out there on a daily basis. Now, with this being a big practical problem, there have been some solutions developed. So let me go over a few of these actually. So the first solution you can think of probably is client-side input validation. So this is a bit of JavaScript sitting in the browser checking values. So this is fine, but unfortunately this is not entirely effective because, an attacker might just be able to craft an HTTP packet rather and send it directly to the application. So this is easy to circumvent. Doesn't work so well. Now the next solution that's used in practice is penetration testing. Essentially it's a black box testing approach that requires a person to come up with potentially malicious inputs in order to either crash or exploit the application. Now, as any testing technique, it's missing vulnerabilities, so we don't consider it as effective, generally speaking. The next technique that is commonly used is something that's called application firewalls. So several companies out there are making devices of this nature. So an application firewall essentially is a piece of hardware that sits on the line and listens for packets that appear malicious. So it needs to be able to understand HTTP and so forth, but it's essentially kind of an intrusion detection sort of system. And as any such system, it suffers from both false positives and false negatives. So we don't like it so much. Now, the final approach, which we like a lot, is code reviews. But the problem is that code reviewers don't like it so much themselves, right? So this takes, this is an effective technique, but it takes a lot of manual effort and it's hard to scale and so forth. And applications, of course, change quite a bit, and so you need to go back. Now, we'd like to automate the code review process. Having said that, let me move on to describing what my work is about. So we call this the Griffin project. This is kind of a catch-all term for the work in web application security we've been doing so far. So I'll talk about, I'll give you an overview of the project. I'll talk about static analysis and some extensions thereof. Then I'll talk about runtime technology and give you some experimental results and conclude. Okay, so this is how it works. The user starts with a specification of the vulnerability. Of vulnerabilities. So they need to tell us what they're looking for. And the application bytecode. So this is typically Java bytecode. These two things are given by the user. Based on that, there is a static analysis being generated automatically based upon the specification. This is something that was first described in our Usenix security paper 2005. And the static analysis runs and gives vulnerability warnings. Now, there are several advantages of this approach, which is it is able to find vulnerabilities early in the development cycle. So that's great. Now, it explores all potential program executions, so it doesn't require any inputs, any test inputs or anything like that. That's also great. And finally, the approach is sound, which means that it's guaranteed to find all of the vulnerability of the sort we're looking for. Now, a significant disadvantage is that static analysis might suffer from imprecisions. It might introduce false positives. Now, since that's the case, we also have an alternative runtime approach. So runtime approach, the dynamic analysis that was first described in our UPSL 2005 paper, essentially takes the application bytecode and instruments it with respect to its vulnerability specification. Okay, so we get an instrumented application that runs alongside others on a standard application server. And the advantages here is that it's essentially not fixing the problems at the core, but it's able to prevent them from doing harm. Okay? Now, another advantage is that it can recover from exploits as they happen in real time, as I'll discuss. And it doesn't have false positives unlike the static approach. Now, the disadvantage is that there is an overhead associated with runtime instrumentation, of course. In order to reduce the overhead, we also have a feedback loop, if you will, from the static analysis. So there's additional static information being computed that reduces the amount of instrumentation that needs to be inserted. And so that's been quite effective in practice equation.
Would you have some numbers on the overhead? I was wondering, since these are more interactive applications, would this matter at all?
Yeah, so the overhead numbers can be, well, they vary, but they can range from about 40% to about 120% for the naive version. For the sort of reduced instrumentation version, drops down to oftentimes to below 10%. It drops down to single digits oftentimes. But I'll have graphs that show that. Besides, these are interactive applications you pointed out, so the overhead is not as significant of a problem oftentimes. Okay, so let me speak to the issue of soundness. I might be preaching to the choir here, but let me make this point nevertheless. Now, there's been a lot of work in bug finding technology in recent years. So here are some of the projects, just a few of them. Now, they go after bugs like finding null dereferences, performance errors, memory leaks, and data races, and so on. And the goal there is to fix and find common bugs that are likely to exhibit themselves in the field. Now, our approach is, our position, if you will, is slightly different. Our goal is to find and fix all problems. And we believe that this is especially important when it comes to critical issues of security. Like I mentioned before, the cost of a single exploit can be very high, and therefore it's that much more important to be able to make guarantees on the results of the analysis instead of just making a best effort attempt. And I'll come back to this. Now let me go back to that example that I had before of a SQL injection. Let me tell you a little bit about what happens within the application as it's running. So this is a conceptual picture. So what happens is that we get some data from the form by calling servlet.getParameter, and this acts as a tain source. Okay, so this is unsafe information flow, also called tain flow oftentimes. And then there could be a string concatenation happening, and then there could be another string operation, and so on. And at some point, this process will hit a sanitizer, at which point this path will stop. Now, I should point out, perhaps, that strings in Java are objects. So each of these things is a separate object on the heap. Now, there could be another path going, right, like this one over here, and eventually it reaches a sink. So once we have a direct path from a source to a sink over here, so the source is something that comes from a web form, and the sink is something that goes to a database, we have a direct path, and therefore we have a potential security violation. Okay, now, initial question here, as it says, is how do we know what all these parameters are? How do we know what this method is and this method and so on? What are these components? Well, we don't. That's in part why we need the specification. So the user needs to tell us what to look for. The user needs to specify what the source methods are, sink methods, derivation methods, which allow us to connect one object to the next, as well as sanitization routines. And the way the specification is provided is by means of PQL. So PQL is also something described in our UPSL 2005 paper, and it stands for a program query language. Now, PQL is a pretty general language for describing sort of many properties of events that happen on related objects. I think that's the most generic description I can come up with. Now, we found it particularly useful for talking about security vulnerabilities. So what I have on this slide here is a very simple query that looks for SQL injections. It doesn't find all SQL injections, of course, but it looks for sort of some types of them. Okay, so this is the query declaration. It returns these two objects, which is kind of the source and the sink in this case. And, well, I'm not going to go through this, but you can sort of hopefully map it back to the code I had in the original application before. Now, I should point out that, like I said before, this is just an example. Real PQL queries are a bit longer than this. They are usually about 150 lines of PQL code, and they're designed to capture all sorts of vulnerabilities, not just SQL injections. Now, the advantage, well, or perhaps a saving grace we have here is that once we write a query like this in PQL, this query is going to be suitable for pretty much any application written to the J2E standard. Okay, so basically the amount of additional specification one has to do for new application is relatively minor.
Question?
Yep.
But you still have a problem, right? If the user makes a mistake in the specification of some source
Absolutely.
method.
Absolutely. I'll speak to that very shortly. Now, having sort of outlined the structure of the system, let me talk about the static analysis aspect of it in more detail. Let me sort of jump right into it. Let me get right to the point. So suppose you have a piece of code like this. Okay, so there are a few lines separating these two chunks of code. So first you get a username from a web form. You add it to a list, and then you get something from a different list, and you pass it to execute query. Okay, you see, sort of, this is an example, but you see pieces of code like this all the time. Now the question is, what objects do these variables, username and str, refer to or point to? Okay, the question is, of course, relevant, because if they might point to the same object, then we might have a vulnerability in this case. Now, what answers this question is a pointer analysis. And a pointer analysis has been a subject of a great deal of research in the last 20 years or so. And in particular, the flavor of pointer analysis that we take advantage of here is the one developed in our group and described in the PLDI 2004 paper. Now, this is a context-sensitive inclusion-based pointer analysis, which sort of these two things are there to increase the precision of it, as I'll discuss shortly. Now, conceptually what happens is that there's a runtime heap, right? And we have some strings and other objects sitting on the heap. What the pointer analysis does is that it provides an abstraction or a static approximation of what's going on at runtime. So in particular, what might happen is that these three objects, so 1, 02, and 03, might map to the same object, to the same static representation or the age. So this represents a collision or an imprecision in pointer analysis. So whenever a precision such as this is introduced, it may lead to false positives, which we don't really like at all. And what we end up doing is we end up developing a bunch of features of the pointer analysis that we built into pointer analysis that increases precision. Okay, I think I said that. Now, there's been a variety of different pointer analysis techniques suggested. So we start essentially with the baseline of a fully context-insensitive pointer analysis. That's generally pretty imprecise. Now, we can add context sensitivity on top of it. I'll discuss what it is shortly. And that's the version we use is described in PLDI 2004 paper. That's still not enough. We end up adding object sensitivity improvements on top of that, and we also have a flavor of map sensitivity, all of which will be discussed very shortly. So this is kind of our ladder of precision, if you will. Okay, so context sensitivity, this is kind of the standard example of why it's necessary, right? So we have two values coming into this function ID that just returns its parameter. So the first value is tainted, the second one is not. If we pay attention to what the contexts are, we'll return this value to the first context and sort of the appropriate value to the second context. There'll be no imprecision, everybody will be happy. Now, if we are oblivious to context information, of course, we'll be less happy because we'll have to conservatively conclude that this value might be tainted. So what happens is that imprecision in pointer analysis leads to excessive tainting, and that leads to false positives. So that's something we would like to avoid as much as possible. Now, in terms of pointer analysis, this is something that can be formulated by, so the points to relation is typically described as a relation between a variable and a static representation of a heap object. So these are the domains here. And this is a context-insensitive relation. Now, context-sensitive version of this is the same relation augmented with a context over here. So essentially parameterize it by context. Now, unfortunately for us, well, while this is much more precise than before, unfortunately for us, this is still not precise enough for what we want. So consider this example over here. So suppose you have two strings allocated over here, and you have two maps, map 1 and map 2. Sorry. So you proceed to put the first string into the first map and the second string into the second map. And then you proceed to retrieve something from the second map. So of course what you want to get from the static analysis is that only the second string could be potentially retrieved from the second map. But we're not so lucky. So the context-sensitive pointer analysis will conclude that either of those strings could be retrieved. Moreover, if you think about that, any string that might have been put into any map declared anywhere in the program will be potentially coming out of this map. So this is grossly imprecise. We don't like that at all. It actually kills the precision of our analysis pretty much completely. So remember, this was the context-sensitive pointer analysis formulation over here. Well, fortunately for us, there is an object-sensitive pointer analysis formulation that was proposed several years ago by other researchers. And So the good way to think about it conceptually is that it parameterizes, instead of the context number, it parameterizes this points to relation by what this object in the method where v is declared is pointing to. Okay? Now this is just one flavor of object sensitivity there is. There are others. So for instance, this is something that's called one-level object sensitivity. So there are two heap objects by which this relation is parameterized on the variable, and there is one on the heap. We might imagine still more precise versions of pointer analysis, such as this, which combines context sensitivity with one-level object sensitivity we had before. Now, this is great. I mean, this is amazingly precise pointer analysis. We like it so much. And it works and gives us perfect results on the small benchmarks that we ran it over. Now, that's the good news. The bad news is that it doesn't scale to anything beyond about 300 classes or so. Now, in Java, your Hello World program is about 250 classes, so you can sort of imagine that this is not the most scalable technique. So we had to get around this somehow. So the approach we use is one of judicious call graph inlining. Okay, so the idea here is that if you inline selected allocation sites, it will give you much more precision. And we kind of know what to inline for the most part. So we know that the internal presentation of containers such as hash map, vector linked list, and so on has to be inlined. The same applies to string factors like string to lowercase and so on. And the precision of this inlining technique is essentially giving us results that are equivalent to those obtained through object sensitivity. Again, this is the good news. The bad news is that, well, first of all, we need to know what to inline. We cannot really inline everything. That's just impossible. So, and we have this tension, right? If we inline too little, we'll get false positives. We don't like that. If we inline too much, the resulting program will be just way too large for us to analyze successfully. So it doesn't scale. So what we have is effectively is an iterative process where we sort of choose targets for inlining, and if it doesn't give us precise enough results, we inline some more. Well, there is still bad news to come, which is in the presence of recursion, there is no particularly good way to do inlining. And when we have virtual methods with more than one target, it's also, inlining is possible, but it's a bit of a challenge. So those are kind of the things that go against this scheme a little bit, but it's still pretty effective, as you'll see. Now, let me talk about sort of the last precision improvement that we implemented as part of our static analysis. It's our sort of pointer analysis phase of the static analysis, if you will. So consider an example like this. So we have a username over here that is obtained from a form. Then we put it inside of a map over here. And then we proceed to get something from the same map. Okay? And then we pass it to this sink over here that we don't like so much. Now, the pointer analysis will happily conclude that since these objects have been placed inside the same map, well, they might be related, therefore we have flow from over here down to here. So it will report potential security vulnerability in this case. But as you can plainly see here, there is really no connection between these two keys, right? So username is not equal to search query. They have no relation to each other. There is no reason why we need to have flow between these two things. So it turns out that this is not just a single example, right? This is something that is actually happening quite often in large Java applications. So this is kind of a poor man's version of structs, where you have a constant string and you associate values with that constant string, and then you retrieve something back from the map at a later point in the program. So we decided to just treat these constant strings in a separate manner. So what we do is we augment the pointer analysis. And it really doesn't take much of an augmentation. It really takes, I think, three or four additional pointer analysis rules. And we essentially model these put and get operations within hash maps in a more precise manner, so that we only have flow between values associated with the same key of a map. Okay, and I'll show how this helps us a bit later on. Okay, so let me summarize what we've done on the front of pointer analysis. So this is kind of a hierarchy. So as far as context sensitivity, we are doing pretty well. So what we are implementing is essentially infinity CFA, which is actually quite a precise version of context sensitivity. With respect to object sensitivity, we are not doing nearly as great. We are doing something that can be characterized as partial one-level object sensitivity, but only applied to certain location sites, but it gives us the results we want. As far as map sensitivity, we are only doing constant keys because this is what we found to be important in experiments, but one might imagine doing much more precise symbolic type of analysis of key values and so on. As far as flow sensitivity, well, our point analysis natively supports, natively understands local flow. It doesn't confuse, it has this local SSA representation within methods, so it doesn't confuse values there. Now, what we are totally oblivious to is predicates. We are not looking at predicate values at all, and that's to contrast with what some of the other groups tried. And again, we didn't really find predicate information to be very valuable in our experiments. And that I should also point out that the analysis we are doing is essentially global, whole program, fully interprocedural analysis. Yep.
So you mentioned that constant keys and local flow seem to be sweet spots for the applications you looked at. Is that also true for the one-level object sensitivity? Because I could see going beyond one level might...
Yeah, so I would be cautious of making that claim. I think there's quite a bit of allocation side bearing happening in some of these things. So you have a factory deep down and you push out. So I'm not making that claim. I think object sensitivity, as I'll discuss, is very important still. Yeah? Sorry?
Can you please say a little bit more about what is local flow sensitive? Is this your terminology or is this the standard one? And is this just SSA conversion or is it more than that?
It's just SSA conversion. I mean, basically, so if you have, the way, something very simple. So the way to understand it is that you essentially have kind of a, what do you call it, a 3-address representation for the method, right? So basically, to make sure that that registers whose life ranges are sort of unrelated don't get confused. That's basically it. There's nothing more than that here. Okay.
So what is your sense of about, is this much flow sensitivity good enough for these kinds of applications, or would you have gained more if you...
Yes, our sense is that. I'll talk about that. Yeah, that's exactly our sense. So, okay, now having described the point analysis, let me give you a little bit of a glimpse of what's going on sort of in the bowels of the system, if you will. And this is just a glimpse, I guess. So what we start with is the pickle query. This is the same example that I had on several slides ago. Now, this pickle query is translated into a query in datalog magically. So there is a syntax-directed way to do translation to datalog. Okay, datalog is this logic programming language, and it's been used, among other things, for pointer analysis tasks. For program analysis tasks. Now, this query in datalog is fed into a datalog solver. So this datalog solver is something that's been developed within our group, and we used it for a variety of applications, and this is among them. So out of the datalog solver, we kind of get two sets of results. The first one is a list of relevant instrumentation points. This is something we'll use for runtime a bit later on. I'll show you where that goes. And the second one, which is something we've been after all along, is vulnerability warnings, so vulnerability traces. And the vulnerability traces are essentially given to the user in a way that they can sort of browse through them and understand what the steps are. So essentially, it's a bunch of traces from a source to a sink with some objects in between. And so that maps directly to what we have here, right? So we have, in this case, a trace consisting of 4 different objects, and the user can go and look and examine the code and figure out what's going on. Okay, so let me come back to the issue of soundness. I really want to beat this point to death. Now, soundness is kind of the only way for us to provide guarantees about the security posture of an application, which is what we like a great deal. Another advantage of soundness is that it allows us to remove instrumentation points, runtime instrumentation points, without jeopardizing the protection that we have at runtime. Now, here's the claim we have as far as soundness is concerned. Our analysis finds all vulnerabilities in statically analyzed code that are captured by the specification. Okay, well, sounds great. Now, there are two caveats to this. Let me show you what they are. First, the first one is this. So we need to figure out what to statically analyze. And the second one is that, which is captured by the specification. As you pointed out, if the specification is lacking certain methods, portions, then we have no way to know what to look for. So both of these are kind of substantial problems. Let me talk about the first one, which is an extension of our static technology. But before I do that, let me actually sort of go back one step and talk about sort of how generally these static analysis in Java operate. So to be able to analyze the whole application, we need to know what the call graph is like. Now, the way this works typically is that we specify a bunch of routes, and then there's a call graph discovery process that runs. So there are a bunch of edges, there are a bunch of call edges being followed here until we reach a fixed point in this process, in this exploration. Okay? And, so remember this picture. Now, here's what the architecture of a typical typical application server with applications on top of it looks like, right? So we have the application server sitting here, and then we have a bunch of applications alongside each other. Now, any of these applications can be perhaps 500,000 lines of code, counting the libraries. The application server such as JBus, this is actually a pretty precise number, I went and counted, is about 1.5 million lines of code. Combined together, this is over 2 million lines of code to analyze. And remember, we're talking about global and hopefully precise analysis. So this is a pretty difficult challenge we have on our hands. So we'd like to avoid it as much as possible. So fortunately, there's a trick. The trick consists of this. The trick consists of looking at this little web.xml thing. So web.xml is a deployment descriptor, or to put it differently, a contract between what the application server expects and what the application provides. And it's usually a piece of XML, looks like this. Okay. Now, essentially what we do is we parse this XML descriptor and we generate a harness that proceeds to invoke different parts of the web application in turn, like this. I'm not showing the details of that, but you can sort of imagine it iterating over all of the servlets and so on. Now, this is a much much better deal we have, because we essentially only analyzed about 500,000 lines of code, all counted, a bit on top of that, but it's still possible. Now, this is kind of as far as finding the roots. Okay, so this harness essentially provides roots for our analysis. Remember, the second sort of piece of the puzzle was discovering the call graph. Yeah.
What's the harness replacing the application server?
Effectively. Yeah. So it sits. So instead of the calls from the alternative would be to start with the main method of the application server, and to analyze it sort of from the bottom all the way up to the application. And in this case, we are cutting it at this level, and that's the harness. Now, the second piece of the puzzle, as I started alluding to, was we need to be able to discover the call graph. Now, there have been numerous algorithms for call graph resolution in object-oriented code. All of those, unfortunately, have avoided the issue of reflection. And reflection, it turns out, is actually very common in large contemporary applications. It is the ones written in Java. And there are multiple sort of reasons why one would want to have reflection in place, including loading plugin code, avoiding incompatibilities, and so on. So this example over here is actually something that tries to create a class over here that's only something you can do on macOS 10. And then if that fails, then there's a different, there's different processing code that's invoked. Now, just focus on this for now, right? So we create a class, and then we create a new instance of that class. So there's a pattern here. So the pattern looks like this. So we get the class name from somewhere. It could be constant, could be something else. We create a class object out of that class name. We proceed to create a new instance of that class on line 3, and then we cast it to some useful type and proceed to do something with it afterwards. Now, the question, a natural question to ask here is, what object is created over here on line 3? Well, there are kind of several ways to go about answering that question. The first one is to figure out what class name is. So this is a string. So where does it come from? Well, there are two potential answers to that. Could be constant, in which case we are golden. We know what classes are being generated over here on line 3. Or it could be a specification point. A specification point is a place in the program where user input is required to fully resolve this construct. Okay, so when everything is a constant, then there is no input that's needed. Once there are specification points, the user, so basically we apply a little bit of pointer analysis here still, and backtrack, essentially we tell the user where this class name comes from. And it's typical for it to come from files, from, from the network, from whatever, from input and so on. But at least we are able to tell the user where the specification is necessary to fully construct the call graph. So this is one approach. And by the way, sort of this approach and others are summarized in our paper in A+ 2005. The second approach is to pay attention to what's going on line 4. So we have a class, we have a cast rather on line 4. Now, assuming we know what all the subclasses of class T are, it could, and assuming of course also that this cast doesn't fail, we can conclude that the object created over here on line 3 is only one of the subclasses. Okay, so this is sometimes imprecise, but this gives us a way to get an upper limit, if you will, on what could be constructed on line 3 over here. So a combination of these two approaches actually proves to be quite effective. So here are some numbers. So we applied this reflection resolution technique, or set of techniques rather, to a set of 6 large Java benchmark applications, almost 200,000 lines of code combined. So this is what we observe. So this is, the blue bar is kind of before, with no reflection resolution whatsoever. And the greenish bar is the after picture, which is with full reflection resolution enabled. So as you can see across the board, there are pretty significant increases in the size of the call graphs. Here we're counting the number of methods. Seems to be a pretty easy way to count the size of the call graph. Now, for some of the applications like this one, for instance, JGAP, the size of the call graph increases as much as 7-fold from the version that we have over here that does no reflection resolution to the one that does full reflection resolution. So the takeaway message here, I think, is that when we sort of pay attention to reflection, the call graph sizes, the call graphs increase a great deal. Or to put it differently, if we are oblivious to the issue of reflection, we are ending up missing a large fraction of the program. Okay, so let me switch gears now and talk about the runtime analysis portion of this work. Okay, so let me remind you what the situation is. So the situation is this. We have the application in terms of bytecode, and we have some sort of vulnerability specification. These things are combined together to produce an instrumentally secured version of the application over here. And this secured version is deployed alongside other unsecured application on a standard application server and just runs as well. Now, there are essentially two ways in which this can be used. So the first one is we detect a potential vulnerability, a potential exploit going through, and we stop, we halt the application. The second mode which is much more attractive for many scenarios, is we detect the application and we are able to recover from it. And we give the user the opportunity to provide recovery code for us, as we'll see shortly. Now, the way instrumentation is done is actually in a pretty generic fashion. So the pickle specification is converted into a series of a set of state machines that run alongside the program that is instrumented. And as I mentioned before, recovery code can run before a match is detected. So there's some sort of a starting event, and then there are other events that are being observed. And what happens at each point in this picture is that partial matches are being collected. So some of the partial matches will never lead anywhere, but some of the partial matches will essentially lead us to a complete match. So in scenario number 1, we stop the application completely. In scenario number 2, we have some sort of sanitization code that we run before we allow this sort of flow to go through, and then we sort of complete this process. Now, let me talk about sort of the final piece of the puzzle here, which is reducing the instrumentation overhead, something you were asking about before. So this is the same old pickle query I've been showing here all along. Now, just pay attention to this matches part over here, right? This is the thing that has to sort of happen at runtime. Imagine a piece of code looking like this. So basically, there is a static analysis that runs and figures out which of these statements over here can participate in a match. And in this case, this code will be able to conclude successfully that only 4 out of 7 statements over here could be part of a match, and the other 3 are just not instrumented at all. Now, as I mentioned before, soundness is something that allows us to safely remove instrumentation points without the fear of sort of compromising the security of the runtime system. Okay, so having described that, let me now focus on the experimental results we get. So there are 2 suites of benchmarks that we use for our experiments. So the first one consists of 11 large benchmarks. So they're quite substantial applications. When we count the libraries and all the other stuff, this is how much code we get, over 3 million lines of code for the big ones. There's also a suite of a bit over 100 micro synthetic benchmarks that I just wrote for the purpose of essentially, testing our techniques. And they contain quite a bit less code. Now, we get we collect information from our work, from the Griffin project, as far as both of these sets of benchmarks are concerned. Oh, by the way, I forgot to mention that these are publicly available, and we have a workshop paper on these if you're interested. Now, in addition to doing that, we also have something else, which is we were able to get a commercial tool that is designed to look for some of the same problems. And we were able to run that commercial tool alongside our approach. And I'll show you some of the comparisons a little bit later. So this tool is called CodeAssure, produced by Secure Software out in Virginia. And these people were nice enough to allow us to sort of show these results. So I'm very grateful to them. Now, okay. So here are some statistics as far as the large benchmarks are concerned. So to give you some idea what some of these benchmarks are, many of these are Blogger applications, or sort of large infrastructures for creating blogs, I guess. So something interesting to look at here is the sizes of these applications. So this is the number of lines of code in the application code itself over here. And this is the expanded number of lines of code. What I mean by that is that when we look at the call graph as discovered by our analysis, and when we count the lines of code within the libraries as well as the application, we get a picture that looks like this. So the lines of code of the application itself kind of are about, 50,000 lines of code, something like that. But the amount of code actually analyzed is quite a bit higher than that. So in the biggest of our benchmarks, Roller, the amount of lines of code analyzed was over 500,000. So I think it's important here to be aware of this difference between the application lines of code and the lines of code that are analyzed. Now, so these are the results. Okay, cool. So this is what we find when we run sort of our techniques on these benchmarks. We find close to 100 vulnerabilities altogether. Now, there's only one of the benchmarks that exhibits false positives, and actually, it has quite a number of them, and I'll speak to that issue in a moment. So, one of the applications has false positives, 147. And here's a classification of the vulnerabilities we find. So there is, so the way this classification works is that there are sources of data, there are a number of techniques in this arena, and there are sinks. Again, there are a number of, there's quite a variety over here. So the most common issue is actually the one that I had in this example before, which is SQL injection caused by parameter manipulation. This is the highest number in this table, but there are other possibilities as well, such as path traversal and cross-site scripting and the like. Now, we reported these issues back to program maintainers, and most of them were actually sort of very nice to work with, and most of the vulnerabilities were confirmed and fixed in later versions of the code. And we got some vulnerability advisories rather issued for this, so we're happy about that as well. Let me now talk a little bit about the micro benchmarks that we have here. So the way this works is that there are different categories for the micro benchmarks. So as you can see there are benchmarks that go after the handling of collections, for instance. There are benchmarks that test the handling of interprocedural code. There are things that have to do with pointer aliasing and data structure handling and strong updates and so on. Okay? So in particular, what I'm emphasizing here is that, for instance, we are finding sort of all the vulnerabilities. Our technique is conservative, so it's finding all the vulnerabilities present, for instance, for these two classes of benchmarks. But at the same time, the fact that we are not disambiguating between array elements and we are totally oblivious to predicates means that we are also reporting a number of false positives on both of these fronts, if you will. Now, none of them seem to be very important in large applications, so I just wanted to point out something that seemed to be important based on our experience with small benchmarks, but not large ones. Okay, so we've spent so much time beefing up our pointer analysis and our static analysis technology. Well, did it pay off? Let me give you an example of what happens. So this is one of the sort of medium-sized application from the sort of real-life benchmark suite. So here's some statistics. It's about 50,000 lines of code. It has almost 400 classes. It has 40 sources. Has almost 30 sinks. It actually contains 6 confirmed vulnerabilities. Now, what I'd like to discuss here is false positives. So when we have sort of a totally dumb analysis that is not context sensitive, no nothing essentially, that's our base number. We get 114 false positives. When we apply context sensitivity, we get it down to about 84. When we apply object sensitivity improvements, we get it down to 43. When we apply map sensitivity, we get it down to 5. And finally, when we add portions of the original specifications that were missing when we started, we get it down to 0. So as you can see here, all of these sort of precision improvements that we've been working so hard to put in actually pay off, at least in some of the applications. And there's this interesting interplay between them, but all of them prove to be necessary at some point. Okay, now, so let's talk about the issue of false positives and false negatives because, well, let's just do that. Okay, so here's something I would like you to focus on. So this is these are the macro benchmarks and these are the micro benchmarks. Now, what we are summarizing here is the number of vulnerabilities, first of all. And we're comparing the results we get from the Griffin project, which is our work, comparing them to the results we get from CodeAssure, which is the commercial tool that we were using. So Griffin is shown in blue, and CodeAssure is shown in green, or greenish. Now, as you can see across the board, for both the big benchmarks and the little ones, we find considerably more vulnerabilities with our approach than they do with CodeAssure. Now, that's great. We like that very much, right? Because we have a conservative static analysis technique. Now, something that's not so great is that we also have more false positives. So in this case, that single application actually bumps up the number of false positives we report quite a bit. Now, their number of false positives is actually very low across the board. It's actually low. It's considerably lower in the case of micro benchmarks because they make these various precision improvements to their analysis.
Can I ask a question?
Yeah.
So are you really comparing apples to apples here? Because I guess to run your tool, you need these vulnerability specifications. And does the CodeAssure tool take the same specs, or what's
Well, so that's. Oh. Let me put this on. Right, so that's actually a valid question. And so basically they don't have, well, obviously they don't have the same sort of input format, if you will. It seems like the range of vulnerabilities by just looking at the tool and sort of they have a way to select which ones to look at seems to be similar. In fact, theirs is actually a superset of ours because they're also looking for some stylistic issues and some memory leaks perhaps and some data erasures as well, so we didn't sort of compare across those types of scenarios. But it seems that they're looking at the same types of issues as far as the web application vulnerabilities are concerned. But there is no way to know for sure whether it's, I mean, it's a point well taken, I think. Now, so a different way to interpret these results is that CodeAssure essentially reports a bunch of false negatives, right? So while our approach is conservative and suffers from false positives, theirs is in a way optimistic and suffers from false negatives. And when it comes to security, the point here is that it's important to be conservative. But I think it's a point I made already, so you know that. Now, let's talk about something else, which is so there's this sort of controversy about shallow bugs versus more deep bugs and how difficult bugs are to find and so on. So let me speak a little bit to that issue. So one way to get at this is by looking at the length of vulnerability traces we find. So here's a histogram, which for each, so remember from the static analysis we get a bunch of traces that essentially sequences of lists of objects, right? So for each length of a trace, we count the number of traces that we encountered in our large benchmark. So you can see here something that is rather surprising, which is there's actually a pretty large number of traces that are quite long. And this is something we found we weren't really expecting. So it's natural to sort of have a bunch of shallow problems you can probably find with, you know, sort of grep or something like that. But it turns out that there are actually problems that are quite a bit more profound. And the longer traces are typically, the more difficult it is to find with manual inspection. That's the point here. Now, there is something else here, which is, suppose I discount all the library code. Suppose I move that, I take it out of consideration. The picture changes. So without the library code being considered, so the longest trace is actually 7 or so. So it's a common pattern for these problems to actually be nesting, if you will, deep inside library code, as we'll see on. Yeah.
How did you count the length of a trace? Is it the number of lines of code, or it's
no? It's number of objects, right? So a trace is object 1, object 2, object 3, object n. You take n and add to the histogram. The other point, which I'm sort of skipping over here, is that there might be multiple ways to get to the, so if you have a source and the sink, there are oftentimes multiple paths that take you there. So that's another sort of factor there. You had another question? Or? No. Okay. Fine. So libraries, right? Okay. Now that gets to sort of this other issue, which is what is the connectivity between sources and sinks. And so here's a picture of a spaceship. No, here's a picture of a graph that we extract from sort of one of these benchmarks when we apply our static tools to it, called personal blog. So the things on the left over here are sources, and the things on the right are sinks in yellow. Okay, and sort of each of these little dots is an object, or a static representation of an object, right? Remember, everything here so far is static. Now, there is more structure in this, as you can probably guess. So here's the structure. So this little portion over here corresponds to application code. This portion over here, which is actually very tightly connected, is library code. So in this case, this is the Hibernate library, a library that's used by quite a large number of large Java applications for persistence purposes. And this little location over here is an injection vector. So this in particular is something called session.find, which is a method in the public APIs that takes a string that is eventually passed to a backend database. And actually there are quite a number of ways for it to go to backend database, as you can see from here. But the fact that this method is an injection vector is never advertised. So there's no way for the user of this library, for this application over here, personal block, to know that they need to sanitize values that go into this API method. Okay. Now, while we're able to deal with personal blog quite nicely, we're not able to deal with this other benchmark called Roller quite so nicely. So what happens within Roller is that it actually happens to use the same Hibernate library as personal blog does. Now, it uses different API entry points from personal blog, and what happens is that there is some falsely tainted object that sort of, no matter what we do, no matter sort of how much call graph cloning we apply, we were unable to make it untainted, if you will. And so that leads to a large number of false vulnerability paths, right? So essentially this one object is responsible. Since you see the connectivity here to be like this, if you have an object sitting over here that's falsely tainted, it will be connected to a large number of sinks and potential large number of sources as well, which leads to this multiplicative explosion problem in the number of false positives. Now, what plays to our advantage, of course, is that if we know the structure of the problem, if we know how sources and sinks are connected, if we kind of, instead of just giving lists back to the user, if we give them a graph or some sort of other hierarchical representation, then the user has a much better chance of figuring out sooner that certain things are false positives. So I think this is something we need to take advantage of here.
Question?
Yep.
So how did you figure out what were false positives and not? Did you go through each of them one by one? Or?
It's hard. So in this case, we knew how to group it, and then basically because I really wanted to get to the bottom of this one in particular. I basically I figured out the entry points to the library, separated the library, wrote a wrap around it, and just stopped it in the debugger to see what path are taken. Seemed to be the easiest way to do it, but of course nothing that a user would welcome, as you can probably guess. It's not excessively easy sometimes to figure out whether something is a false positive or not.
One question?
Yeah.
So does this mean in some sense that you're counting the number of false positive wrong? Maybe you should count the number of falsely tainted objects instead of the number of traces they generate?
Well, so yeah, the issue of counting. So there are many ways to go about it, and people have sort of tried different approaches. And in this case, we're just counting combinations of we're counting sourcing pairs as one. We're not. If we were counting paths, then things that are very, very sort of that are roughly the same thing would be counted as multiple ones. The idea here is that the number of pairs roughly very roughly approximates the amount of manual effort one has to invest to inspect these results. Right? Because, I mean, like I said, because of this sort of joint connectivity among paths. That's the approach we chose, but there are alternatives to this as well. Okay, now sort of the long-forgotten runtime analysis. Well, so here's what happens here. So we basically installed a bunch of these applications on a standard application server. Their instrumented versions were installed. And we, first of all, the first sort of sanity check, if you will, we took some of the results we got from static analysis and turned them into exploits. And we ran these exploits against these instrumented applications. And we are happy to say that we are able to block and recover from these exploits at runtime. So that's thing number one. Then the next interesting question to look at is the question of runtime overhead. So what happens here is that, well, the naive implementation essentially ends up instrumenting pretty much every string operation there is in the program. And trust me, there are a lot of string operations. So the overhead can be somewhat significant. So as you can see here, for instance, for webcode, the overhead is more than twice, right? So 140% on top of the original execution time. And for some of the others, it's around maybe 40% or so. Now, when we apply, when we compute static information and reduce the number of instrumentation points, first of all, the number of instrumentation points drops considerably, sometimes to almost 1% of the number of original instrumentation points. But secondly, of course, the runtime overhead is reduced dramatically as well. So in this case, rollers are winner with the runtime overhead being pretty much negligible. But in other cases, the runtime overhead is also quite good. So for webcode, we have something about 40%. And as I mentioned before, these are interactive applications, so the overhead is not as significant as it would be in a batch type or server type environment. Okay, so let me talk, first of all, let me summarize the contribution. So I think you know this by now, but let me just sort of emphasize a couple of points here. So I think what's been driving this research to a large extent is the desire to solve a large, important real-life problem out there. And we essentially came up with a hybrid approach to do that, which consists of a static analysis. And focusing on static analysis technology allowed us to push the technology quite a bit further than it was pushed before, in particular in the area of point analysis precision, as well as scalability, and also looking at features of modern applications such as reflection. The other aspect of this was smart runtime technology and sort of providing the ability to recover from exploits at runtime. So moving towards better, more friendly runtime environment has been the theme for that. And finally, we sort of drove a lot of this with a large-scale experimental validation of our techniques, which, first of all, like I said, allowed us to push the techniques quite a bit and led us to the discovery of a large number of previously unknown vulnerabilities, which is always a good thing. So as far as the related work, well, there is a great deal of related work in the field of bug finding and software verification. I'm not really going to cover that because that would take me quite a long time. Let me. So I already talked a little bit on the subject of penetration testing, as well as application firewalls, that are some of the commonly used techniques in this area as far as web application security is concerned. So people have sort of applied various testing technologies to that. Now, there are several projects that were inspiring at the time we started our project, which was the WebSARI work that was done in the context of PHP. Essentially, the techniques there are quite a bit different. So PHP is a scripting language, and the technology there needs to be sort of appropriate for the language they're analyzing. Now, there is no sort of soundness guarantees that they're making, and but still, I mean, they found it to be quite effective for what they were looking at. There are a couple of other projects, sort of, for instance, the JDBC checker project was kind of an interesting project. It focused on precisely analyzing, sort of statically figuring out values that can be part of Java strings. But again, we think that the focus there is a little bit misplaced. I think if we are able to follow strings precisely, I think that's kind of most of the problem right there. Now, what happened is that we were actually lucky enough to publish a lot of to publish sort of the big 2 papers in the Griffin project quite a bit, pretty early on, in early 2005. And what happened, at least sort of academically speaking, is that there was an explosion in the number of papers that came after that. So we got a lot of citations out of that work. So people have sort of looked at various extension of runtime technology. People have also looked at, including some groups at Stanford, looked at analyzing PHP and other types of scripting languages. People have even looked at better client-side protection technologies, so instrumenting, sort of following JavaScript in the browser seemed to be actually a pretty profitable, pretty interesting idea to try. So people have looked at that quite a bit. So there's a URL if you're interested. So there's, the amount of work in this area is still small enough to fit in one page. Okay, so let me talk about some of the projects that sort of naturally emerge from this style of research. So these bars over here indicate the sort of progress, if you will. I don't know how to measure progress, but this is my best sort of intuitive guess. So one of the areas in which we made quite a bit of progress actually is applying model checking technology to some of the same issues. Now, the focus of my work has largely been on sort of what happens when there is a single HTTP request that comes down the line and goes into the application, something happens to it. Now, there might be other interesting issues that happen when you have multiple interacting HTTP requests that the application receives, or there might be data that is preserved from previous requests that is affecting the current one. So this is where model checking technology is believed to be attractive. Another sort of good feature of this model checking technology is that essentially it's able to derive full exploit traces. So we run the model check, it comes back with the answer, and the answer is essentially a snapshot of every turn through the application code. And that actually makes it very easy to explain to the user what went wrong. Unlike our approach, which actually requires a little bit on the part of the user to sort of figure out what the flow of data is locally. Another interesting area in which we made also quite a bit of progress is learning specifications from runtime data history. So our experience has been that it's common, especially in object-oriented systems, to have a single piece of data that might be contained in an object at one time, but is then extracted or permuted in some way and put into another object. And if you look at that piece of data across time, I think you will learn quite a bit about what valid and invalid behavior might be. So people have looked at method calls, for instance, applied to a single object and try to construct state machines that describe and capture that sort of interaction. And so that work has been quite successful, but we believe that we can go quite a bit further if we focus sort of on data as it migrates from one object to the next. Now, as far as the program analysis, sort of the underpinnings of the program analysis technology is concerned, I think there's quite a bit of interesting work still to be done. So I mentioned before the data log solver. The name of the data log solver is BDDBDB. And we applied it within our group to a lot of interesting static analysis problems. But now I think we're at the point where we don't really have a good way to scale it anymore. So basically, some of the problems we threw at it lately have been essentially hitting the limits of that technology. And there are different ways to go about that. One of them is sort of this other project that we started, which is using partitioned BDDs to scale the solver. And let me just give you a glimpse of that. So BDDs, the idea there is that you essentially achieve high levels of compression when you have information that has a lot of commonality in it. Now, in order to do that, we need to figure out how to, so BDDs operate on large bit vectors. And we need to tell the BDD package what order the vectors need to be in. Now, the problem is that there is no globally good order. And it often happens that if you separate the problems into chunks, and if you run the chunks on separate processors, you'll be able to find locally best orders on those processors. And each of the processes will complete sooner, and then you'll be able to combine the results. At least that's the hope. And there's been interesting technology developed at Fujitsu Labs that applied this separation sort of technique successfully to hardware tasks. We'd like to adapt some of this to this problem as well. There are, let me see, which ones should I pick? So, okay, let me just mention one more of these, and then we can go to questions. So this one, for instance, is, so the way we've been doing analysis lately in our group is by essentially in a declarative fashion, which is we take the input program, we represent it as a set of relations. It's essentially a database. And then we have a data log program that constructs relations out of the input relations which are stored in that database. Now, when we finish that process, when the data log sort of query runs, we have the results. And then if we're able to classify the results as false positives and true positives, then perhaps we can go back to each and revisit each individual decision that we made sort of within this process and figure out whether it was a good decision or not. So if we have an oracle that tells us what the false positives are, we can go back and figure out what the sources for the precision are, and perhaps learn where it is best to enhance the precision of the analysis in the first place. And there are many other things which I'm going to skip. So let me, this is pretty much all I have. So these are some of the relevant URLs for the Griffin security project, and then some of the benchmarks, well, actually all of the benchmarks, in fact. And then the PQ language, which I'm kind of downplaying because it's the work of my co-author. And there are also sort of papers on some of these things. I'm out of water too.
Any questions?
Yes.
So I'm not too familiar with the area of web applications, but did you ever run into the problem of concurrency or multi-threading?
Yeah, well, so the point analysis we use is flow insensitive. So it's essentially oblivious to the ordering of the statements we have in the program. So it wasn't really even an issue for us.
But did you use SSA? So I'm guessing SSA won't work out right for concurrent applications.
That might be a good point. Well, so it's the same sort of assumptions that the pointer analysis is essentially using. I don't know. I'll need to sort of think about this as an issue a little bit. There might be something there that is not as obvious. Yeah.
To what extent would your techniques extend to a language that's not typed?
Well, so we did a project in C. Actually, one of the things mentioned here that was looking at format string vulnerabilities and formats. And buffer overruns. And the idea there was essentially similar, which is you statically analyze stained. And well, the flavor of pointer analysis ends up being very, very different. So even though you can imagine reusing many of the same sort of framework features, if you will, the underpinnings are very, very different. So it really applies to, I think this technique applies best to type-safe languages and to the flavor of pointer analysis that has a clear distinction between variables and heap objects. Because in C there is really no such thing, and you have structs located on the stack, and you have other nasty aspects of the language that really make it quite a bit harder to analyze, and that results in worse precision sort of down the line, if you want to be conservative, of course. We looked at a couple of ways to do point analysis in C, one of which was fully conservative, if you will, and the other one was a bit more optimistic, and we kind of define what it means. But for the optimistic one, yeah, you essentially get more precision, but you see what the tension is there. Yep.
So I want to understand a little bit more about your interest in using model checking for web applications. So currently you're using this information flow analysis with a fancy pointer analysis, and as you showed that the number of false positives was quite clear. So with model checking, do you want to cut down these false positives, or are you looking at more richer specifications?
Well, I think the focus there is slightly different. It's not my project, so I can't really fully speak for it. But first of all, so I mentioned a couple of things, right? So one of them is sort of having a full trace of an exploit, and there's actually being able to craft an exploit, which we give to the program maintainers, of extremely high value, right? Because, I mean, basically, the way you do this stuff is that you sort of stare at what you get statically, and then you end up sort of coming up with the exploit yourself. So if instead of that you had a full automatic way to have an exploit, perhaps also with the value that would exploit, which is actually the focus of that research, finding values that would be able to exploit that, such as that it's actually fully aware of the, of the branches in the program, and the value takes the right branch. So that by itself is of great importance oftentimes. Now, the other thing is that we were sort of limiting our scope a bit, which is we were sort of looking at a model in which we have a single request arriving, and then the idea is that if you have interactions of multiple requests, as you typically have in the running web application, then you might have these interesting corner cases. So one user would place something in a global data structure, which would at a later stage would be consumed, would place a tainted value in a global data structure, which would be consumed by somebody unknowingly pulling out of the data structure, right? So you can see that playing out as well. But I think sort of most of the focus is on coming up with interesting exploit values. And there's been a lot of interest sort of in at Stanford, in Dawson Angler's group, for instance, in coming up with sort of inputs that crash the application. So we are looking at some of that same some of those same problems over here. So sanitizers, for instance, is an interesting area. So the story there is that sanitizers are essentially, most of them are routines that take a string and return a string. And the string they return is some derivation, some variation on the original one. They would filter some of the characters, they would do some other things. And the problem is that essentially, in order to do this right, since we have taint input pretty much in all of these applications, application writers end up writing sanitizers. And there are no good standards as to how to do that. So everybody ends up improvising. And pretty much everybody, with only a few exceptions, gets it wrong. It's actually a very challenging task to do it because there are different complications such as encodings that the input takes, and making sure that you use the right set of characters and that you use whitelisting instead of blacklisting and so on. It's quite a challenging problem, turns out. And in some of the cases, so for some of the problems we found, we ended up essentially constructing exploits that went around some of the sanitizers they had in the first place. So the sanitization that was there was insufficient. That's part of the reason why delegating specification to the user, because we cannot really ensure sanitization in any good way. But on the other hand, model checking seems to be a suitable approach to breaking sanitizers. And the other thing is that we can actually afford to have a great deal of precision, because most sanitizers are actually very self-contained sort of pieces of code. If you're interested, I can show you a couple. I don't know, depends on. Okay, sure.
Table further questions, and thanks again.
Thank you.